In the last video, we discussed what a column vector was. A column vector is just a matrix with one column and n rows. Let X be a column vector and A be a square matrix of n rows, just like the column vector X. Suppose that when you multiply the matrix A by the column vector, any matrix, it is as if you had multiplied it by some number, which we will discuss later. We'll just call it lambda for now. Lambda is a number. The left side is matrix multiplication. The right side is multiplication of a matrix by scalar. So suppose we want this equation to be true. Now subtract lambda x from both sides, and then we're not factoring out an x. What we're doing is we're just taking it out, and when you do, that leaves you with a minus lambda. However, a minus lambda is incorrect because you can't subtract a number from a matrix. So to make this correct, what we do is we say lambda times I. Lambda I is a unit matrix of order n. So in order for this to be true, a minus lambda I determinant must equal 0. And this is an algebraic equation. A minus lambda I equals 0. Lambda is called an eigenvalue of this matrix. So an eigenvalue is a special number which is the solution of this equation. This equation here is called the characteristic equation of matrix A. For example, take this matrix, this square matrix. If we want the determinant of A minus lambda I to be 0, that means minus 3 minus lambda 2 minus 3, 4 minus lambda is 0. And it's going to look like this. Minus 3, 2, minus 3, 4, minus lambda I. And I is 1, 0, 0, 1. So this will be minus 3, 2, minus 3, 4, plus minus lambda, 0, 0, minus lambda. So this will be minus 3 minus lambda, 2 minus 0, which is 2, minus 3 minus 0, which is minus 3, 4 minus lambda. That's this equation. In effect, what you will be doing, you don't have to go through these steps, just subtract lambda from the diagonal terms. So minus 3 minus lambda, 4 minus lambda. The other two will stay the same. Make it a determinant and set it equal to 0. So we'll do the determinant. Minus 3 minus lambda times 4 minus lambda minus minus 3 times 2, which is minus 6, equals 0. Simplify this equation and you'll end up with lambda squared minus lambda plus 6 equals 0. This is called the characteristic equation of matrix A. Let us factor it or solve it somehow. And when we do, we end up with lambda minus 3 times lambda plus 2 equals 0. The solutions of this are lambda 1 equals 3 and lambda 2 equals minus 2. Here they are. So this matrix has two eigenvalues. An n by n matrix always has n eigenvalues. They could be real, they could be complex, they could be repeated, they could be imaginary and conjugate, they could be anything. So the eigenvalues are lambda 1 equals 3 and lambda 2 equals minus 2. For the eigenvectors corresponding to these eigenvalues, each of these eigenvalues is going to have an eigenvector. Now to find the eigenvectors, we start with lambda 1 equals 3. And let's call the eigenvector xy. Substitute back in equation 2, which was this equation here, minus 3 minus lambda. So lambda equals 3, so minus 3 minus 3. Here's the eigen characteristic equation. Here it is. So minus 3 minus lambda, minus 3 minus 3. 2, 2, minus 3, 4 minus lambda is 4 minus negative 3. Times the vector x, which is xy, should equal 0. So again, minus 3 minus lambda, 2, minus 3, 4 minus lambda, all of that times xy equals 0. Okay, put the eigenvalue here, and you will end up with negative 6, 2, negative 3, 1, xy equals 0. First equation will read minus 6x plus 2y equals 0. Second equation will read minus 3x plus 1y equals 0. So if you look at the second equation, we can take 3x to the right side, and that will give us y equals 3x. In y equals 3x, we're free to choose x or y, choose any number, because we're only looking for the direction of the eigenvector. I'm going to pick x equals 1. So we have y equals 3x. If I pick x equals 1, then y equals 3. So my first eigenvector is 1, 3. I'm going to write it here. The eigenvalue was 3. The eigenvector was 1, 3. Let's do the same thing with the second eigenvalue. The second eigenvalue was lambda 2 equals minus 2. So put it back in this equation. Minus 3 minus lambda, which is minus 3 minus 2, 2 minus 3, 4 minus lambda, which is 4 minus negative 2, times xy equals 0. Simplify this. This will be minus 1, 2, minus 3, 6, xy equals 0. First equation is minus x plus 2y equals 0. The second equation we don't need. It's minus 3x plus 6y equals 0. We only need one of these equations. If you have a system, a 3 by 3 system, you can reject one of those three equations and use two of them. So when you solve this, you end up with x equals 2y. This time I'm going to pick y equals 1 and x equals 2. So x equals 2, y equals 1. That means my eigenvector is 2, 1. So I'm going to write it over here. Lambda 2 equals minus 2 and vector v2 equals 2, 1. So the eigenvector corresponding to the eigenvalue lambda 1 equals 3 is 1, 3. The eigenvector corresponding to the second eigenvalue lambda 2 equals minus 2 is 2, 1. Could somebody have picked different numbers? Yes. If somebody had picked x equal 2 here, their eigenvector would have been 2, 6. If somebody had picked 2 here, their eigenvector would have been 4, 2. The important thing is to have these. In the end, when we solve a differential equation, I'll explain to you how these don't matter. Like whether you pick 1 or 2 or whatever number, it doesn't matter. Why are we doing these eigenvalues and eigenvectors? Here's why. When you're solving a system of differential equations, looks like this. dx1 dt equals right side. dx2 dt equals right side, etc. All the way to dxn dt. The unknown vector is x1, x2, x3, x4, all the way to xn. So these are the unknowns. The left sides have the derivative of the unknowns. The right side may have x1, x2, x3, etc. If we only have two unknowns, we'll just call them x and y. But if we have more than 3 or 4, then we can call them x1, x2, x3, x4, etc. So this is a system of differential equations. Okay, if you remove the unknowns and pick only the coefficients, then the coefficients are a11, a12, a13, etc. This is called the coefficients matrix. The differential equations system is dx dt equals ax. The entire left side is just d capital X dt. The right side is capital A times capital X, where capital X is the unknown. But remember, X is this vector. So we call this unknown vector capital X or capital Y. If you see capital X or capital Y, it means more than one unknown. The procedure for solving this system is like this. When you have a system of differential equations like this, identify A, the coefficients matrix. It's always going to be a square matrix of order n. N is the number of unknowns you have. Find the eigenvalues of that matrix. Lambda 1, lambda 2, lambda 3, all the way to lambda n. And also find the eigenvectors of that matrix. V1, V2, V3, etc. If the eigenvalues, case 1, the eigenvalues could be real numbers and different. They could be complex, they could be anything. Let's suppose they're real. If they're real, then the solution of the original system, this system here, is capital X equals C1 V1 times e to the lambda 1t plus C2 V2 e to the lambda 2t plus C3 V3 e to the lambda 3t, etc., where C1, C2, C3, etc. are constants. That's why if you get a vector V1 like this, 1, 3, and somebody else gets a vector 2, 6, it doesn't matter because you have the constant here. You have not determined the constant yet, so C1 times 1, 3 or C1 times 2, 6 are the same. In the earlier example that we did, we had found these for the eigenvalues and the eigenvectors. We got lambda 1 equals 3 and V1, and we had lambda 2 and V2. So a solution of a system with those eigenvalues and eigenvectors would be this. Capital X equals C1, 1, 3 e to the 3t plus C2, 2, 1 e to the minus 2t. I'm going to show you an example which leads to these eigenvalues and eigenvectors. Here's the example. Suppose we're solving this system of equations. dx dt equals minus 3x plus 2y. dy dt equals minus 3x plus 4y. First, take the coefficients matrix, identify it. Minus 3, 2, minus 3, 4. Here it is. We did this earlier, and we found the eigenvalues to be lambda 1 equals 3 and V1, lambda 2 equals minus 2 and V2. So therefore, the solution of this system here, the general solution, would be capital X equals C1 times 1, 3 times e to the 3t plus C2 times 2, 1 times e to the minus 2t. Remember, capital X is x and y. So that means xy is equal to C1 times 1 e to the 3t plus C2 times 2 e to the minus 2t. Small y is C1 times 3 e to the 3t plus C2 times 1 e to the minus 2t. And if we were to write x and y separately, it would be x equals C1 e to the 3t plus 2C2 e to the minus 2t. Y equals 3C1 e to the 3t plus C2 e to the minus 2t. After we do this, we cannot change these constants. This constant would have to be 3C1 and this would have to be 2C2. So we can't change it to C2 because these constants are functions of the eigenvectors. If somebody had picked a different eigenvector here, like 2, 6, their constant here would be 2C1, 6C1. But once you pick numbers for your eigenvectors, keep them. And this is the general solution of the system. If they give you boundary conditions, they would have to give you 2 to be able to determine the constants C1 and C2. This completes the recording for the case of real and different eigenvalues.